Given the charge configuration using Coulomb's law and the associated and required integral, line or surface or volume integral, or Gauss law, we can determine the electric field intensity at any point. We can determine the electric field intensity at any point. And if you know the electric field intensity at any point in the field as a function of the coordinates of that particular point, we can determine the potential difference at any point in the between any 2 points in the field. Potential is as such a scalar quantity because it is the work done. If we can define the scalar electrical potential at any point because of a point charge, carefully listen now. If we can develop an expression for this electric scalar potential at any point because of a point charge, using scalar integral, single integral, not one integral for each component. Using scalar integral, we can determine the potential at any point in the field. If you determine the potential at any point in the field and give the general expression for that, the same electric field of the charge is given as scalar field. If potential is the target field quantity to be determined, it is better to develop the potential directly because of a distributed charge. So to get that potential at any point, no, it is not the potential difference. Potential at any point due to a point charge. Q. Assuming it to be positive. For positive only we will do, but substitute the charges with their polarities to get the actual value of it. Potential. Absolute potential it is. What is this? It is the work done on 1 Coulomb unit positive charge. Mathematical. Otherwise, you have to understand it as on a small positive test charge per unit of the charge. In bringing it from the point where its potential is 0 to the point of interest. Due to a point charge Q. What is the 0 potential point in the field of a given point charge? It is the point where any charge kept at that point doesn't move by itself. If the object has some potential energy, if you leave it, it starts moving from that position naturally in the field. If I keep an object at a particular point in the region, if it stays there only without moving, we say its potential energy is 0, freely kept without any support. If you just leave it, it should be there only. That is the 0 potential point. Any point where when I keep the charge, if it starts moving, is the non-zero potential point. It is the work done on 1 coulomb in bringing it from the point where its potential is 0 to the point of interest. Check it now. If I have a charge of 2 coulombs, where can I keep any other charge so that it doesn't move? I should keep it at a point where the force experienced by the second charge is 0. What is the charge? Infinity. Correct? If I take a point which is at infinite distance from the given charge, q by 4 pi epsilon d square d equal to infinity is 0. So, keep checking. If I consider a point which is at a distance d from a point charge, potential at that point V, not VAB, V is the work done in bringing a unit positive charge from infinity to the given point. Again is the field force. Naturally, again is the field force. Potential difference being, I told you, in any practical field, potential difference between 2 points is only the point function, not the path function. I'll come to that also. Now, I will consider a simplest path. I want to determine the potential at this particular point. I will extend the line and go to infinity first. Let us say this is positive x-axis. I want to know total amount of work done in bringing unit positive charge from infinity to the given point. Integral x is equal to infinity to d. Carefully look at it. Minus. Along this line, dl bar is what? E bar is what? What is E by? Q by 4 pi epsilon x squared at any x. Ax. You agree this? At any distance x, the electric field intensity is q by 4 pi epsilon x squared Ax. You agree this? This is E bar. Along x-axis dl bar is dxax. What is this value now? Q by 4 pi epsilon integral infinity to d minus 1 by x squared dx is q by 4 pi epsilon integral minus 1 by x squared is 1 by x, correct? From infinity to d, which is q by 4 pi epsilon d, so many volts, because I consider 1 coulomb of charge. Is it fine? Now, listen carefully. Suppose I consider an imaginary spherical surface of radius d, having the center at the given positive charge, point charge. What is the potential at any point? Everywhere on this spheric sphere, I know that the field is perpendicular to the sphere, radial. From this point, which is at a distance d, if I move to any point on the sphere, what is the potential? Still the same. Q by 4 pi epsilon d. From any point at infinity, you bring it nearer to the sphere. Point, charge. You come onto the surface of the sphere. Straight away towards the charge when I come. From there, if I start moving on the sphere of radius r, what is E bar dot dl bar for any path on that? Because on the given imaginary sphere of radius d, electric field intensity is everywhere perpendicular to the surface, because of which that particular surface will become equipotential surface, between which the potential difference between any 2 points on that particular surface is 0, because of which q by 4 pi epsilon d is the potential at any point on the sphere of radius d having the charge q at its center. Check it, please. This is potential. Let the potential at any point which is at a distance d from a point charge of q coulombs is v, given by q by 4 pi epsilon d. Because of dq, it will be dv, correct? You agree this now? If it is a differential amount of charge, potential is also differential, because dq tends to 0, q tends to 0, v also tends to 0. Both are differential. Point charge dq coulombs is dv volts. Now, our target here is only to put the integrals. If I have a line charge with charge density rho L, I will consider a point. I will consider a point. What is the potential? How to calculate the potential at this point because of this line charge? A general element on this is of the charge rho L dl at any L. And the general distance is r. It's not a vector now. Distance only is required for me. The formula is scalar. What is the potential at this particular point? V is equal to integral rho L dl by 4 pi epsilon r. General distance is r. General charge is rho L dl. In the integration, I would have considered all point elementary line charges and added the potentials at that particular point because of each elementary charge. Correct? So any finite charge distribution, if I am given with, practically I will not have infinite charge distributions and all. If any finite point charge distribution is given, if it is distributed on a line, it is rho L dl only, pakka. With charge density rho L being uniform or non-uniform. If I have a surface on which charge is distributed with charge density rho s, then at a general ds and the point of interest from a general ds is at a distance r. It's possible When it is possible to talk about a vector, I can always talk about the magnitude of the vector from a general point to the point of interest, and that magnitude of the vector is R. What is the potential V at this particular point? V is equal to double integral rho s ds by 4 pi epsilon R. So many, this surface charge is considered to be the combination of infinitely many infinitesimally small surface charges. I will take a general element, general distance, and then vary the coordinate. No, basically it is a double integral because I am there in a surface. The same way, if it is a volume charge in the given coordinate system, I will consider first of all a dV. Rho v dV is the charge. From that, the point of interest is at a general distance of R. And the potential at that particular point is triple integral. All are independent variables of rho v dV is the point charge divided by 4 pi epsilon R. So many volts, so many volts, so many volts. In a system of units. Any finite charge distribution given, at least mathematically we can say it is possible for us to determine the potential at any point using the potential at any point because of a point charge. Check it once. V is integral dV ultimately. Whether it is rho L dl or rho S ds or rho V dV is dq. dq can only produce dV. Total voltage if I want, potential at a point, I have to integrate dV. Which is rho L dl by 4 pi epsilon R single integral, or rho S ds by 4 pi epsilon R double integral, or rho V dV by 4 pi epsilon R triple integral. Is it clear? Let us not worry about it. For finite charge distributions in general, it is possible so I am considering only those cases where it is possible to derive the expression for the potential at any point as V of xyz or V of rho phi z or V as a function of r theta phi, depending upon the coordinate system in which we are there in. Normally, depending upon the configuration, right? We will select either the Cartesian coordinate system or cylindrical coordinate system or spherical coordinate system and determine the potential at any point in the field, which is the region in the space given. Carefully listen. In the course of our discussion, we came through electric field intensity to potential. Then we derived the expression for the potential at a point because of a point charge, like we defined the expression for the electric field intensity at any point because of a point charge. When I can define the potential at any point because of a point charge, I can straight away determine the potential at any point because of a distributed charge. and describe the given electrostatic field as the scalar field. You agree this? Because you are describing it by giving potential at any point. If we know the expression for the potential at any point in the field, it is possible to determine the electric field intensity at any point in the field. It is possible to determine the electric field intensity at any point in the field as the negative of the gradient of potential at any point. Negative of the gradient of potential at any point. Very good thing actually for us. Check it now. Now the discussion is gradient of a scalar function. Of the spatial coordinates for the sake of development function of x, y, z in general. Scalar function. Now listen. In the Earth's gravitational field, we talk about the potential of an object. At any point which is at a distance h from the surface of the Earth, we say the potential, scalar potential is mgh, assuming that it is now z-axis mgz. Do you agree this? Height, when I want to talk about height, it's z. Where at every point in the field, weight of it is what? This is actually gravitational field force mg bar in the downward direction. This is potential as a function of z. Correct? At the point, I will move from that particular point through a distance dl. Please keep telling. From this point, if I move through a distance dl to the right, what is the change in potential? To the left or in any direction on the plane, horizontal plane at that height z. On that, wherever you move, potential is same. Along these paths, dv is equal to 0. You agree this? Because we are there on horizontal plane, which is considered to be equipotential surface. Next, if I move through this particular distance, again dl only in that direction. Let us say this is theta. I have effectively moved through dl cos theta against the field. some small dV I will get. But if I move it exactly in the opposite direction, it is maximum dV, correct? For the same dl in different directions, the change in potential is different. For this also dV, for this is big dV, vertically upward direction. If I come down, it is minus capital D, big dV. This is minus dV, correct? This is minus dV. You agree this? dV in general is actually what? From the vertical, if I've defined the angle, dV cos theta. dl cos theta. Proportional to dl cos theta, it will be dV, correct? Now, listen now. I am there at any point, at some point. If I move through a distance dl from that point, let dV be the change in potential. This change in potential dV for the same distance dl moved is different for different directions in which we move. You agree this? There is only one particular direction along which for the same dl there is maximum change in potential. Only one particular unique direction. The maximum space rate of change in potential. The maximum space rate of change in potential given by delta V by delta L, limit delta L tending to 0, because I want to talk about at any point, gives the magnitude of the electric field intensity E bar, and it occurs in the direction opposite to E bar at that point. This maximum space rate of change in the potential is called as gradient of potential. Normally gradient is slope. Normally you know that gradient is slope, but gradient is here is maximum slope, maximum space rate of change in potential is called as gradient. And that gradient is equal to the magnitude of electric field intensity at that point, electrical wise. And it occurs in the direction opposite to the electric field intensity. Because of which E bar is minus del V, we call it. Here, carefully see this. So, gradient is what? Del V or del bar V vector. Gradient of scalar del bar V, and E bar is equal to minus del bar V. E bar is equal to minus del bar V. Please check whether this is clear or not. Now I will explain. In the gravitational field, mg is the downward force. Actually, when I move exactly in the opposite direction to mg, change in potential is mg dl is dp. For the same distance along horizontal line is zero potential change. Correct? Downward it will be negative change. Maximum means what? It should be positive change that it is maximum. For the same distance dl moved, only for the vertical path, change in potential is maximum. Along vertical line, along, right? Vertically upward line. dp by dl is maximum in that directions only, which is equal to mg, correct? What is the weight actually minus of mg is, mg bar is minus of dp by dl max. Occurring in one particular direction. So you have to understand the gradient as, okay, mg is actually mg is dp by dl max, and actual direction is minus of. Max occurs only in a particular direction. Gradient is what? Maximum space rate of change in the potential is the gradient of potential. At any point, negative of the gradient of potential, it's actually vector, because it occurs only in a specific direction. Negative of the gradient of potential at any point is electric field intensity. Proof is simple. We know that dV, the change in potential, change in any function, V as a function of x, y, z. dV is what? Dou V by dou x into dx. Dou V by dou y into dy, we proved it. Dou V by dou z into dz is a total differential. When you know the V is a function of x, y, z. dV is what? Dou V by dou x into dx plus dou V by dou y into dy plus dou V by dou z into dz. This can always be written as, carefully say this, dou V by dou x ax plus dou V by dou y ay plus dou V by dou z az dot dx ax plus dy ay plus dz az. You agree this? I know very well that it is equal to minus E bar dot dl bar at that point. At any point. At any point. The derivation is fixed. It's only one step derivation for us, like this. Right? The total differential dot product, because it is E bar dot dl bar is this. This expression should be equal to minus E. So E bar is equal to what? Minus of dou V by dou x ax plus dou V by dou y ay plus dou V by dou z az, called as minus del bar V. Just for the sake of talking about it. Let V at any point is x y squared z cubed, just for the sake of talking about so many words. Let V at any point be x square x y squared z cubed voltage, because it should depend ultimately on the coordinates of the point. Let this be the function. I want to know, find V at 1, 2, 3, VA, VB at minus 1, 2, 3, and E bar at 1, minus 1, 2. V at 1, 2, 3 is what? 1 into 2 square into 3 cube. So many volts. 108. What about this? Minus 1 into 2 square into 3 cube. Hey, is it 108? Minus 108.
Yes, sir.
VA, VB are 108 and minus 108, because I took them like that. What is VAB? 216 volts. Because it is VA minus VB. B is at lower potential, A is at higher potential. B to A, if I come at work, VAB is 216 volts, VBA is minus 216 volts. I want to get electric field intensity at any point. E bar is equal to what? At any point. B at any point is there. Somebody gives you a point, you directly substitute it, the coordinates, and then get the potential. What is E bar? E bar is minus of dou by dou x of x y square z cubed ax plus dou by dou y of x y squared z cubed ay plus dou by dou z of x y squared z cubed az, which is equal to minus of y squared z cubed ax plus 2xy z cubed ay. Please check it now. Y squared z cubed ax, 2xy z cubed ay, next, plus 3xy squared z squared az. This field for sure conservative. We will understand it when you go to current. Okay, wait for that statement anyway. This is the electric field intensity at any point E bar minus of gradient of potential at 1 minus 1, 2, what is it? E bar at 1 minus 1, 2, the point is minus of minus 1 squared into 8 minus 8 ax. You agree this?
Sir.
Next component, 2 into 1 into minus 1 minus 2 into 8 plus 16 ay, correct? Minus is there outside. Next one, minus or plus now? 3 into 1 into 1 into 4. Minus 12 is it? At a point, coordinates given, it's constant.
Volt per meter.
Yeah, it's volt per meter. So many volt per meter. Unit also volt per meter because d by dx of v, d by dy of v, each has a unit of volt per meter. No, whenever I want to determine the electric field at any point because of a distributed charge, best procedure is what? Going through V. It's just differentiation only. Integral is one scalar integral. If I want to directly find out the electric field intensity, I have to evaluate 3 different integrals. One for each component. Because voltage is a scalar quantity, using a scalar integral, single, double or triple depending upon the configuration. It's a scalar integral. Ultimately, to determine electric field intensity, one scalar integral and one differentiation. Better actually. Now that just because wherever you want to measure electric field intensity, it is measured through potential difference, because of which the unit of it is volt per meter ultimately.